Hello, everyone. Good morning, good evening, good afternoon. My name is Kannan, Muthukkaruppan, one of the co-founders at Yugabyte. And my pleasure to welcome you all to the YugabyteDB Friday Tech Talk series for engineers, by engineers. And our guest today is Krishna Sunder. I would love for him to introduce himself. He's been on this series before with other topics. Maybe, Hari, I'm forgetting which one it was, but I think it was like auto flags and things like that. But why don't you share a little bit about yourself, and we can jump into the topic as well.
Thank you, Kannan. Hey, folks. My name is Krishna Sunder. I've been here at Yugabyte for almost 2 years now. I work on the DST team, which is the storage layer of Yugabyte. And I primarily work on xCluster, auto flags, upgrades. So yeah, my previous 5 DTs have been on auto flags. I think I did one on leader preferences, so I can set leaders in two regions. Yeah, that's what I've been doing here at Yugabyte for the last few years. Before that, I was at Microsoft for almost 10 years, and I worked on Azure SQL DB and Azure Synapse Analytics, so cloud databases again. And I've done a couple of different things: logging, recovery, metadata storage, sort of the same storage level stuff there as well. So yeah, that's the briefing of myself. And yeah, can we get started, correct?
Yeah, let's get started.
So today we're going to talk about transactional xCluster. So this is a particular flavor of xCluster that we introduced back in 2.18, where we provide transactional guarantees. And I'll cover that in the next slides. So before going into what xCluster is, just looking at Yugabyte, so Yugabyte provides a couple of different deployment options to get strong, resilient consistency and failure domain tolerances. Right? So the two broad categories you can think of as a single region multi-zone deployment, where we have nodes all in one region, like in this example here, all in each region, A, B, and C zones. So a couple of things is Yugabyte is consistent during partition failures. So we are CP database, which means we need to have quorum commit models, and we need an odd number of replicas to establish quorum and do quorum commits, so that we are consistent across partition failures. So when you go to a single region deployment with multiple zones, what you get is consistency across the zones. Your write latency is slow because you're only doing your network response within one zone, which is usually very quick. But you're only safe against a single zone failure. If your region goes down, then your DB is unavailable. And what you get with 3 zones, you can tolerate a failure of 1 zone. Versus the other thing that you can do is multi-region. You have 1 node in each region, so you're going to have 3 regions, and then you can tolerate an entire region going down. So in this example, I have east, west, and central. So if central were to go down, the DB would still be fine because you still have east and west remaining. The drawback here, though, is that your write latency is not going to take a hit because the network latency between east and west is maybe 60 to 100 milliseconds. Go from Europe and US or India, it's even more. So your write is going to take a hit there. Also, you need to have 3 regions in hand. So if you're doing on-prem deployments, then you don't have 3 regions, then this is not possible. You can also have the multi-cloud thing, but I'm going to skip that part here. So this is what you get with Yugabyte in general. And that's why xCluster comes in. So xCluster offers you to run with 2 regions. And in this deployment model, this is the regular xCluster without transactions. Right? This has been there for a few years now. What you get is you can deploy 2 clusters, one in region A and another one in region 2. And the region 1 cluster is going to have its own 3 zones, so that you get strong, consistent writes within that region across those 3 zones. And similarly with region 2, you have 3 more zones here, so you're consistent within that region. And you have xCluster now doing an async replication between the 2 regions. It could be unidirectional, it could be bidirectional, it's up to you. And if it's bidirectional, you can write on both sides and read on both sides. Unidirectional, you can read on both sides. So you get a bunch of these deployment tools.
But Hari, it's fair to say, I think maybe you're going to compare and contrast the non-transactional and transactional soon. But in the non-transactional case, oh, okay. Go ahead.
What do you get at xCluster? Right. Yeah, I'll cover. So with xCluster, you're going to get async replication, which means there's a delay between writes showing up on the other region. But the advantage is that you don't have any write latency or read latency. And your writes on one region, the writes are going to be quick. It'll take a few extra milliseconds or seconds to show up on the side. And you get durability because of the 3 zones that on each region that we talked about. You get isolation, the regular one that you get Yugabyte, and xCluster doesn't interfere with any of that stuff. So the fact that you have xCluster in there doesn't reduce your isolation guarantees. And xCluster scales horizontally. We'll cover this a little bit more later on. But what that means is that more nodes you add, the more workload you add on one side, xCluster will also scale. So it won't be a bottleneck for bigger clusters. It's fast. And like we've done a lot of optimizations to make it fast. So I wanted to call that out. So things that are like with async replication and with the non-transactional mode, you're going to get eventual consistency, which means across tables, data is going to flow in over time. So you may see data on one table, but not another table. Same with indexes and such. So it will be eventually consistent. Give it a few seconds or milliseconds. And there is, if you're doing bi-directional and you're doing active-active multi-master, you can write on both sides. But that means last writer wins policy is used, which is great for a lot of applications. But one thing with last writer wins is that it means it's a silent overwrite of data. So you have to be careful with that. But yeah,
the last bullet, when you say multi-master, you're basically referring to the bidirectional writes.
Right. Yeah. This exact thing. The like full-blown xCluster, everything in the that you can deploy. Yeah. You can write on both sides, and if both sides you touch the same row or the same key, then you get last writer. If they're operating on different key ranges, then you're fine. So there's no impact.
But I think it's generally fair to maybe summarize that generally the non-transactional xCluster is more suited for, it has to be used carefully because it's more suited for the simpler kind of NoSQL-like use case where you don't have cross-shard or cross-table consistency requirement in this async pipe, right?
You're right. When you're doing the recon, yeah, in the entire pipe.
Yeah.
So that's where xCluster comes in. So it's gonna everything after fast is the new stuff. So with transactional, you get everything you got with non-transactional. Plus now you get atomicity and consistency guarantees and global ordering. So you get the entire ACID rules. Everything's in that, right? I'll cover more about how we get that and what those means. But yeah, now with atomicity, consistency, and global ordering, which means that like the Postgres workloads, the SQL workloads, you are going to get table level guarantees, indexes, foreign keys, any relationships, everything will be consistent on both sides. And the advantage of having that is that we can use this for a DR scenario. So you can have disaster recovery now set up with transactional xCluster, and that's going to give you a DR with very low recovery point objective and a recovery time objective. What that means is that if one region goes down, you can quickly fail over to the other region with minimal data loss. And it will be consistent and atomic and all of that.
And in addition to the DR, it's fair to say that, for example, the target and cluster can also be used as a live read replica of the primary cluster.
Right. Yeah. Yeah.
Okay. Sorry.
Yeah.
Yeah, you're covering this, yeah.
Right. So this is the transactional xCluster deployment mode. So here what we have is the same cluster region 1, cluster 2, region 2. So here I have region 1 acting as an active primary region, and region 2 is the active replica region. So they are both active in the sense both can, your app can read from both sides. And the primary side is only the one that you can write in. So app is going to do reads on both sides, and both sides reads will be ACID, consistent, all of that. You get that? You write on this side, and xCluster is going to take care of replicating your writes from this region to that region. And again, it's async, so your writes have very low latency impact. Yeah, but the main thing is that you can do reads on both sides while things are like in stable state.
And
Yeah.
sorry to choose, I mean, maybe if you could comment on which release is this available in, and what does the end user have to do to choose between this mode versus the previous mode? Is that, yeah, could you comment on that?
Okay, we have, I think it's been available since 2018. The docs do cover that, and have a link to the docs in the latest slides. Why would you choose transactional versus non-transactional mode? Yes, I think like you mentioned, the Cassandra-like workloads, the NoSQL workloads, but maybe the cross-table guarantees are not that important.
Sorry.
You could go with.
No, my question was, I think the when to use is understood, but my question was more, how does the end user, what do they need to do to say this is the mode of xCluster that I want?
Oh, how do they set it up?
How do they set it up?
Right.
Are you covering that?
I just put the link in the doc. The doc does cover it,
Okay,
but for OSS, the commands that are used for setting up both transactional and non-transactional are identical. I think the only thing different is during the setup, you have to pass in an extra flag that says transactional. And
got it.
You have to set which is the primary and which is the replica region. Once you do that, it will automatically work, right? So this, and not much overhead. It's, I think, the same commands, just an extra few parameters. Okay. I don't have an example of the command here, but I do. I mean, I have a demo where I set it up already, so I can show that later.
Yeah.
Right. So for the DR case, DR, there has been a YFTT talk about that separately, so I'm not going to go too much into it, but just to go over a high-level overflow. So you can do two things with DR. One is we call it a switchover, where you're switching the two sides. So now with the switchover, region 2 becomes your primary and region 1 becomes replica, and your writes are now going to the other side. So you'd want to do this during planned maintenances, right? You want to do software upgrade, hardware upgrade. So at that time, you can switch the role and then do your upgrades on the replica region, and then switch back and do it on the other side. And it's an instant switchover. It'll be very quick, and both sides have to be up. Versus the other case is a failover. And for failover case, you say if one region fully goes down. In that case, we're going to cut the replication and just say, hey, the old primary is dead, switch over to region 2, and now take writes on region 2. It is important to know that because of the async nature, you will lose a few milliseconds of data, potentially, depending on network latency and other factors in that. So it's not a zero error loss thing, but it's very low and very minimal. That's the trade-off versus just doing a multi-region deployment. And yeah, we had two previous YFTDs, one that covers the regular non-transactional xCluster, it's linked here, and just the DR part is covered in this other one. This YFTD, we're mainly going to talk about how transaction works, the internals of it, right, going into the guts of the system. There's going to be a lot of boxes and arrows. And I'll briefly go over how xCluster in general works. This is true for both transaction and non-transaction. So Yugabyte is broken up into two layers, the query layer at the top and the DocDB storage layer below. xCluster works on the DocDB storage layer, and it works on the vault replication. So the actual vaults that we use to quorum commits and have strong consistent guarantees within a tablet, within one universe, we read from the same vault and we stream that to the other side. And the vaults are per tablet. So it's a stream per tablet. And each of that is independently getting replicated, which is why you get the horizontal scalability. The more tables you put, the more nodes you put, xCluster just like it's per stream. So you just like pick up. And yeah, it's vault replication. We have a lot of optimizations on top to like compress it more and use lesser bandwidth across the regions because there's more network relay here. So there's a ton of work that went in there. But yeah, overall, it's essentially just replicating the log. So for transactional xCluster, what do we need? We need global ordering. So like I mentioned, we are replicating a tablet at a time. And each tablet has its own log, the vaults, right-hand logs, that is getting replicated from the source side to the target side. And it's independent, which means that on the target, each one is either like lagging behind or faster or slower than the other one. So we just go read the tablets without doing anything. I just like, go read this one. I'm going to get times 7 from tablet T and times 6 from tablet T, which is where the transaction guarantees break in the regular xCluster. So what we want is to say, hey, I need a consistent point where I'm sure that all the data is there. So we have this concept called an xCluster save time. And to simplify it a lot, it's just the time at which all the tablets have the data. It's a guaranteed time that everyone has caught up to. So we pick that time. And now any reads that you do to any point in time before the xCluster save time is guaranteed to be consistent and ordered, globally ordered. Right? And yeah, that's sort of, we take the regular non-transactional xCluster, which is doing this replication, and add this xCluster save time on top to give transaction guarantees.
So maybe one way, just to maybe capture what you said and paraphrase it maybe. So fundamentally, all the transaction logs or these write-ahead logs from the source side are being streamed kind of in parallel in near real time. But
right.
If you read from the edge, it's going to be a jagged edge. So there is a
exactly.
safety calculation to make sure that, hey, I know for sure all shards are caught up to this safe time, and doing reads from the target universe, we automatically make sure that those reads are done at a safe time and that the receive percentage. Yeah, thank you.
Right. And also during a DR, this is what we do. If the source side went down, on the target side, we are caught up until the xCluster save time. So we'd go snip the logs from this like jagged edge and say, this is a consistent set. So you have now, your DR failover will go from time 4, this example.
And we just have to drop discard anything outside of that edge.
After, exactly. Yeah, that's how the DR strategy is. Okay. So just doing global ordering actually will give you cost table stuff, but it's not good enough. And to explain why, you have to go further down into DocDB and how transactions in the transaction world of Yugabyte. So again, there's a very deep topic. So there's been a few talks. Mikhail had one about RocksDB. We do have documentation about how transactions work in Yugabyte. It's in the public talks, the links are here. And I will try to do a very brief, very high-level, simplified explanation because I want to focus on xCluster parts. So in Yugabyte, what you have, this is like not even xCluster related, just in general. Any Yugabyte instance universe you take, you have 2 types of writes. You have 2 types of records that you write. It's the provisional records and the regular records. So provisional records are essentially an intent to make a change. And the reason we use that is to get transactional commit across shards, across the tablets, across nodes. So what we do is, I'll go more in detail, but yeah, there's like a provisional record is always tied to a transaction. And to know if that record should be read or thrown away, you have to check the transaction to say, transaction metadata, to say if it's committed or not committed. I'm not going to go into the strong write, weak write, all of the other stuff. We'll glance over that stuff. But essentially, a provisional record has a transaction tied to it, which may and may not be committed yet. A regular record is guaranteed to be committed. And that's all we need to know for now. Now, going to transactions. So transactions are always like got lots of steps in that. So we have an app here that is going to write a transactional write, and it's going to update key 1 to value 1, key 2 to value 2. You can set row 1 to value 1, row 2 to value 2. And we have 4 tablet servers in this example here. So first node that the app connects to is going to sort of act like a transaction manager. And it's going to now, the first thing we have to do for any write, any transactional write, is to start a transaction. So we go to this transaction status tablet. And there's a lot of these things spread across every region, every node. So it's actually very close to where the app is, and this has very low latency. So you create this transaction metadata, and it itself has its own quorum commit logic. So it's persistent. So all the steps in here, everything after this, nodes can fail, nodes can move over, and we'll still be tolerant to failures. So you first create a transaction, and you get the transaction ID. And then what happens is you now do your writes, and you want to write key 1 and key 2. Key 1 has to go to shard 1, which is on T server 3. And your key 2 has to go to T server 4, different shard. Each of them, again, gets its own quorum committed. Each of them is persisted, so you have durability guarantees. And once you're done with your entire batch of statements in your transaction, you have to commit it. So to do the commit, you only have to go to the transaction status tablet. So you go in there and say, now this transaction ID 1 is committed. And then you're done. And then we just go back to the app, and the transaction, as far as the app is concerned, is committed, everything is persisted. So at this point, if you look at tablet servers 3 and 4, these are still provisional records set to transaction ID 1. Someone tries to go scan it, they will resolve the transaction ID and say commit, so they'll show it as a regular value. What happens is asynchronously, this transaction tablet will now do an apply of these provisional records. And the apply is essentially converting them to a regular record and taking that transaction ID out and just saying, this is now committed for sure. And this is like a very high level, oversimplified explanation of distributed transactions in Yugabyte. And the xCluster parts, xCluster works on the user shards. So we replicate whatever is there in T server 3 and 4. We do not replicate the transaction manager. We don't replicate the transaction status tablet, none of that. So what we are going to get is those provisional records and regular records, the applies and the regular records. And the fact that the applies are coming in async means that across transactions, now if you have more than one transaction, they're going to get applied in a different order. So even that is not great for transactional xCluster. So we have to fix that as well. And in order to do that, what we do is that I have a timeline here. The top part is things happening on the source, and the bottom part is things happening on the target. As soon as the provisional record comes into the source, it goes to the target. There's a network delay associated with it, and within that duration, it will flow down to the target. And then after that, the user is going to commit your transaction at some other data point. And every 250 milliseconds, what you do is you batch all of the commits that happened the previous 250 milliseconds and apply all of those provisional records, passed on the apply records, which again is going to flow to your target. So your target doesn't get the commits, but it gets the applies. And now you got a big batch of things that you want to apply, 250 milliseconds, so you have to go apply all of that. And the time that we did all of this is your safe time, because that's what we apply up to. So we remember the time and we keep track of it. And this is per tablet, right? Because all of this is happening at a tablet granularity. Now we have two more. On the target side, you have to get the global ordering guarantee. So we need to compute the global xCluster safe time. So we accumulate all the safe times per tablet, the entire system. We compute that, and then we have to propagate that back to all the Postgres instances, the upper layer, YSQL layer, so that you can now serve consistent read source of that. So these are done again in backgrounds, and for now we have set it to a 1 second interval. But the point to remember is that these two steps are actually independent of the source. So even if the source had to go down at this point, we keep computing that. So the worst we lose is that 250 milliseconds plus network delay of data in the happy part, right? And these are all async going on. Good.
Yeah, thanks, Hari. Yeah, makes sense.
Yeah. So we are at times I'll do a quick demo, and demoing a transactional correct read during write, it's actually harder to prove. So I've tried to keep this simple, but also I'm not a SQL guy. Like I said, I'm a storage guy. So my SQL queries are not perfect. So with what I know, I've done, this is my setup. So I have two tables, a customer's table with an ID, name, and the location, the state they're in. It has a primary key on the ID, an index on the state. So I try to make it a little bit more fancy. So I have an index on the state. And then I have my accounts table, which has an ID and the balance, and I have a foreign key between them. So I have tables, indexes, and foreign key constraints. And all of this has to be maintained in xCluster now. So what I want to do is do a join across all of this and modify all the data and prove that my result is actually consistently correct. So I'm going to run this query, which is essentially get the balance per state, but limit it only to Washington and California. and then union and get all the balance, the total of everything. And if I look at the plan for that, I'm doing an index scan on one place, another index scan here, and a sequential scan of that component. So I'm scanning multiple tables, and each of them has tablets across nodes. So I'm trying to make sure that I touch everything everywhere and prove that, hey, it is.
Did I get it? Did I understand right that the query is trying to do both get the total balance and the balance for Washington and California?
Yeah.
Okay.
That's the. I show an example later on without any workload running. But yes, I want to prove that the total balance is same. Money can't leave the system, and I'm gonna again with my limited SQL thing. What I'm gonna do is I can't just choose sum of states and just move money everywhere, and then it's gonna keep changing. So what I have is 20 accounts, 20 customers, and I have put them in 4 groups, A, B, C, D. So money is gonna move within one group. So ID 1, customer 1 will send it to 5, 9, 13, 17. And we have the same for other groups. And each group is in one state. So I'm going to move money within one group, but I'm going to switch the states that the groups are in. So when I do my previous query, over time I'll cover, and I keep watching that, I'll cover every group over time and prove that within every group, the totals are the same. That's my aim here. And my workload itself, I'm gonna move a random amount between $1 to $10 between 2 customers of one group. So this is like query I have for that. Again, not too great, but it works. And to swap the states, I'm basically picking 2 random states and swapping states with a temporary thing in that. It's transactional commit, so I should never see an NA in the middle, and I should see a transactional swap. So
got it. So basically, you're not moving a single person's state, but
the entire group.
Like you're switching this group state for the entire group. Okay.
Right, the entire group. So within a group, the total will be the same, will never change, and the total across everything will be the same too. I mean, the simple case for this is to not have groups and states and just to one table, but you only get one. You can only prove one table thing. So I wanted to do tables, indexes, and multiple nodes. Yeah. This is why it's a little bit more involved. And let's go to the demo. So I have 2 clusters. I have my what I call East with 1, 2, 3. And I have my West with 10, 11, and 12. 3 T servers on each. And I have my accounts and account balance table. I'll actually this thing. I'm going to do the queries on the West side. On the West is the replica, and the East is the primary. So the writes happen on the East. Reads can happen anywhere. I'm going to show the reads on West. So I have my 2 tables. I'm going to show what I have to begin with, my total balance, right? And I'm doing a join across the 2 tables, and I have 20 customers, 4 states, and each one has 50,000 to begin with. So, and I can show the query plan again. I have my joins with indexes and aggregates. Good. So if I run that query by itself, and what I get is Washington has 250,000, California has 250,000, and the total is 1 million. And I'm going to keep running that in a loop every second, right? So, and then I'm going to run my workload. So what I'm going to do is I'm going to swap the cities, and this thing just swaps random cities of the entire group. It's one chunk. And the other one, I'm going to move the money, and it's going to move random money. And while those are going on, nothing's happening, and that's what we want. We want to see nothing happen. And data is flowing in. If I actually go to the backend node and actually look at my stuff, I can see that records are getting received. So things are moving here on these nodes across all the tables. I'm getting.
This page we are seeing, is it on the target cluster or on the source cluster?
Right. So this entire group is the target. The West one, I'm looking at node 10 on the target, and I can see node 11. I can also go to the source. If I go to the source, I'm going to see outbound stuff on the target.
Got it.
I can see inbound stuff, right? And if I do pause at the right time and do the counts, it should add up.
Yeah.
And so data is moving in, and it's been the same. Nothing's happening, which is good. I don't want anything to change. And just to show that actually things are moving, I can also even query my previous query, right? Here you can see that the balances are changing. Right? Everyone is sort of moving money around. You can do a watch on that too, and you should be able to see, oh yeah, states are changing too. So money is changing, states are changing, but the sum remains the same. It's always transactions. If you pause here, add it up, it'll be transaction.
So I wasn't aware of the /watch command. Does it just repeat the previous command every 1 second?
Right. You can say watch. It's a second level candidate. You can say how much to wait, and now wait every 2 seconds. It's a very nice, neat Postgres command that you can use instead of doing loops and stuff.
Nice. Learned another new trick.
Yep.
Yep. Hari, one question that, and we may have to drop off. Like one question is, if for your use case you're happy with unidirectional xCluster, is there any advantage to still using the non-transactional mode? Is there an overhead? I mean, would you recommend pretty much to go with the transactional mode?
Yeah, if you have YSQL and just have it just go with a transactional mode, there's not much overhead. We've done a ton of optimization on top. Even with transactional itself, I can set a flag that'll actually disable my reads and just switch to non-transactional reads. And if I actually do that, you will get non-transactional data. So I can change my consistency level here. And now we still do the computation, but we're not going to use it. So I can still run in this mode. And if I look at this query now, I should see like non-transactional values.
Okay.
And so you can always switch. You can just set up transactional if that's the only thing you have. I mean, again, here my stuff isn't running too fast, so I can't see it. You can see that even non-transactional is actually, for the most part, it's pretty stable after run it for a while to actually see it.
To catch the failure case in non-transactional may need
maybe I can't do watch and I have to do watch more. When I see
timing sensitive test. Yeah.
It's very timing sensitive. But if you run it in a tight loop, you will catch it a lot of times.
Yeah.
I think, oh yeah, I missed a semicolon. That's fine.
Oh.
Oh, there you go. I hit it once and you can see 1,000,007. Yeah.
Yeah, nice.
Yeah. Okay, good. We got lucky there. But yeah, you always, if you have YSQL and if you only want to write on one direction, you can just go with the transaction. There's not much overhead on that.
Got it. Wonderful. I think we can wrap now. Thank you everyone for joining us for this episode of YFTT. And thank you so much, Hari, for great work on this project and a really nice presentation. Really like the slides and all of that. So yeah, hopefully a lot of folks find this helpful. These talks also go on our YouTube playlist and all that. So it's pretty easy to find all our previous YFTT talks also. Yeah, and see you all next week. Hari, over to you for closing comments.
Thank you, everyone. And just before I'm done, links to, the slides will also be available in YouTube. There will be a link to it. Also, more docs are here. Everything that I demoed, how to set everything up, we have our docs and there should be enough commands there. And Slack channels. If you have any questions, feel free to send a message in Slack.
Thank you.
Awesome. Thank you.